Welcome back to Pragmatic Rust for Engineers. I'm Tim, here with Jonathan, and we're ready to explore deeper into the world of chemical engineering and Rust programming.
It's great to be back. In our last session, we laid the groundwork by simulating the Haber-Bosch process, a key method for ammonia production.
That's right, and you learned some basics in Rust, like functions and data structures, and about traits that allowed us to simulate the Haber-Bosch reaction with an ODE solver. We started with simple kinetic models to introduce differential equations in Rust. It was about easing out these complexities of chemical reactions and Rust.
Exactly. It provided a foundation showing how basic reaction kinetics can be modeled in Rust, setting us up for today's advanced topics.
And today we're going to take it up a notch. We delve into much more complex reaction kinetics, which are essential for a realistic and practical simulation of the Haber-Bosch process. But first we will start with a quick coding section to get the plots running. Jonathan, you've done a lot of work to provide this preparation for the modeling part. Can you show us what we give an overview?
Sure. Today we'll explore the intricacies of catalysts and their profound influence in the reaction kinetics. We're moving beyond the theoretical models we'll initially discuss. And interestingly, our modern understanding of this process didn't fully develop until the 40s, 50s. That's when better experimental data for reaction kinetics and other process variables became available, providing a more qualitative chemical engineering basis for the design of ammonia converters.
Oh, that sounds that we had like a really significant leap in our understanding in this time.
Absolutely. This period marked a pivotal point in the history of chemical engineering. Now, if we direct our attention to this graph, we're looking at the reaction rate of ammonia formation.
Wait a moment, it seems there's going a lot on in this graph. Maybe you can introduce us to the axis first.
Yeah, of course. This graph is a crucial tool for chemical engineers. It visualizes the complex relationship between the temperature of the reactor on the y-axis, the concentration of ammonia on the x-axis, and reaction rate. So the curves labeled with V are the iso rates. Each curve represents a constant reaction rate for the formation of ammonia.
So it's like a map, iso rates are mountain highs, and instead of coordinates we have temperatures and concentrations on the axis.
Yeah, totally right. The line labeled V0 is just the equilibrium state, where no reaction, the reaction rate is zero, so no net formation of ammonia. Let's now assume constant concentration. As you can see, when the temperature increases due to the nature of the reaction, it reaches a maximum point, and then if the temperature keeps increasing, it just goes down. Joining these maximum points will give us the temperature for the maximum rate for each ammonia concentration, and this line runs parallel to the equilibrium line and around 30 to 50 Celsius below.
I got it. I think we have to cool to counter this exothermic reaction, right? So, and this A line, it is like our optimal operating band, but still I would really like to have the relationship to an actual reactor.
Yeah, that's a good question. In practice, we modulate the reactor's temperature profile to operate as close as possible to this A line that you said that is optimal by managing the reaction conditions and the heat exchange. So we want to be about this 30 to 50 Celsius below the equilibrium line. This is going to maximize the reaction rate without overshooting the equilibrium point, where the reaction rate would just drop down. Let me show you a schematic of a reactor.
All right.
Here we have a typical reactor used for ammonia production. What I want to highlight now is how we control temperature along the reactor. We start by introducing a synthesis gas mixture, which is nitrogen and hydrogen, into the system. This isn't just any step. It's crucial because we need to hit sweet spot of temperature to kickstart the reaction. This is due to the activation energy requirements. As we move along the reactor, there are three distinct sections, or what we call catalytic beds. Here's where the magic happens. The catalysts within these beds get to work. As the synthesis gas interacts with it, we see a spike of temperature. This is all part of the reaction's exothermic nature, releasing heat as it transforms our gas into ammonia. But here's the twist. As we produce more ammonia, the reaction could slow down, and we don't want the temperature to get too high. Besides the reaction efficiency, there are other reasons like catalyst longevity and above all operational safety. To tackle this, we cool down the gas mixture as it exceeds each bed. One method is by using external heat exchangers. This smart move does double duty. It keeps our temperature in check and harnesses the excess energy to produce steam, which in turn can be used for power generation. In industry, this is called heat integration.
Thanks, Jonathan. This visualization really helps to understand what is going on in reality.
Great. So, how do we proceed?
We'll introduce a plotter's crate on a simple example. Later we will use the functionality for analyzing our simulations.
Great.
Alright, before we work on the plotting, I will select the task commit. For this, we fire up a terminal and use git k to show our version control. And in the version control, we select the task commit. It may be that there are more commits in your case up above. And then we create a new branch called Iterators where we will work on the solution together. What we now have to do is to use git checkout to switch to the solo branch. Alright, I opened our task description and here we want to update the project structure by adapting the cargo terminal. So when you're ready with this task, it should look like that. We have like our plotters dependency and we have 3 different binaries defined. Like this is the old one for the first video. Here we will be working on our plots and this is the sequential simulation. We will come to this after talking to Jonathan. And what changes now is like when you use cargo run, it cannot be sure what you mean. You have to specify with dash -bin and in our case HP pulse test what it has to run. And here we see hello plot and we will jump into the main plot file. And the first difference you spot, there is a return type, right? So it's a result and in the end we return OK with an empty type and we can also return any kind of error like box has any kind of error, okay? And we will use this in the course of the video now, but let us first get our plotters dependency in here too. And what we do first is we need to get a drawing area. So we have a drawing area, DA, which is based on a bitmap backend that stores its constant to the mypng file and has a resolution of 800 cross 600. And we put this into drawing area and then we want to fill it with a color. Let's say we use red here. Okay, and after that we want to present everything, and if we now compile we can see, okay, there were warnings, but what we also can see, we have mypng. But let us come back to the warnings. There's an unused result, so we don't do anything with the error variant. Fill can fail, and yeah. So there's a warning about it, and what we can do first is like use the question mark, and that means, okay, in the error case we just plop it up, or what you can do is like you can match this, which is a match statement, and then you have like your 2 arms. In the OK case you simply do nothing, okay, we're fine. And in the error case we would just println could not save file. So that's how you work with results. Alright, now we get a plot. Therefore we use a chart builder on our drawing area. And chart builder is a builder pattern. There you can chain methods like margin, like set left and bottom label area, and like build Cartesian 2D, which needs now the x-axis values. So we go from -3, come on, to 3. And from -30 to 30. And we use a question mark and we store on our chart for further processing. And the first thing we do is we configure a mesh which has like the X description outside data and the Y desk magic numbers. We then draw this and do a check. So that's what our myPNG looks like. We should switch to white probably. And the next step is like, how do we get our cubic function? So we need pairs like x and y coordinates. So let chords be, and what we do is we will set up a range, but in Rust you cannot define float ranges. That's why we're using an integer range here. And we use an iterator for this. And an iterator itself is like a lazy object. That means it does actually nothing until you consume it. So we use a map function here, for example, where we take the x. This is a closure. So the function we program is given to the map. And here we just say, okay, we want x as f32 and divide it by 100. And in the next map, we get another closure. This time x is already our float, and we just multiply it. And yeah, so you can see here, that's the wrap type, and there's nothing happening yet. So what we could do is like we can shadow the type and use a function that actually do something, and that is collect. And collect, okay, we have to define the type for this, I guess. We'll collect into a vector of a pair of f32s. And there's a mistake. That's it. So now we have a vector chords which is not used. What we need to do next is, and maybe let me highlight it. That is like nearly no computation power, and now the lazy object gets consumed and something is happening. We store it in a vector, okay? And now we can use the chart and draw a series. We use a line series, a new keyword, give it our chords, and like some color, like let's go for black. And that's concluding our small little plot here. Let's see. Nice. At the end, we have a plot like this and functions for later use. If you want, have a look at the solution or try it on your own. And I would say we should join Jonathan and look at the more sophisticated model next. Jonathan, last time you introduced us to this general balance equation of ammonia. Can we revisit that? How does this lead into a more detailed model?
Certainly. If you recall, we had this general equation where V represents the speed along the reactor, delta C over delta X is the change in the concentration along the reactor, and RA is the reaction rate. Previously, our model was a bit simplified, but now we are aiming for a more accurate depiction of the reaction kinetics.
Right. And how do we achieve a more accurate model?
We use a modified Temkin equation as proposed by Tyson and Simon. This equation considers a more detailed kinetics approach where K is the reverse reaction rate constant, Ka is the equilibrium constant, and A represents the activity coefficients for nitrogen, hydrogen, and ammonia. Alpha is a constant value between 0.4 and 0.75.
I see. What about the reverse reaction?
The reverse reaction is described by Arrhenius type equation.
Okay, I understand. K and Ka are given by those two equations, but what is about these activity coefficients? How do they come into play?
Good question. The activity coefficients are linked to the fugacity of the components, which account for the non-ideal gas behavior and their high temperature and pressure conditions of this process. Fugacity, the Fi, is a thermodynamic concept crucial to our understanding of real gas behavior.
Okay.
But let's put it in simple terms. As you might remember, partial pressure is equal to the total pressure times the partial fraction, right? So the non-ideality is introduced as a coefficient that multiplies this partial pressure. So this coefficient is called the fugacity coefficient.
So fugacity is like another part of our more detailed model, but how is it exactly calculated?
It's calculated using these equations, which describe the fugacity coefficient for each component. These coefficients helps us correct the ideal gas assumption by considering the real conditions inside the reactor.
Oh, that's quite much formulas. This really underscores the interdisciplinary nature of chemical engineering. It's not just about reaction engineering, is it?
Not at all, Tim. As you're aware, our chemical engineering combines multiple disciplines. It draws from thermodynamics, reaction kinetics, fluid dynamics, and more. This integration is crucial for successful modeling, design, and operation of processes like Haber-Bosch.
Right, and I think you're making a very valid point there. And especially for those viewers who are more familiar with programming and not with chemical engineering, maybe it seems like always the same complex mass. But that being said, in our last video, we talked about modeling with a three-dimensional state vector: nitrogen, hydrogen, and ammonia. How does it change with our additions?
That's a great question. We're now adding more components to our model. Inner gases like argon and methane, plus we can't forget the variations in temperature within the reactor, which dramatically affects the reaction rates. Imagine it's like adding more layers to a program where each layer interacts with each other.
Oh, I really like that. Jonathan, I remember this simple schematic of the plug flow reactor you showed us in the last. But what would be seen in industry?
Indeed, the reactor concept is a PFR, so plug flow reactor. However, in industry we have different types of PFRs, such as the packed bed reactor. Today, the objective is to maximize heat recovery and minimize costs within the synthesis loop, which requires effective heat removal and so as conversion proceeds.
I see, yeah. So what exactly do you mean by the synthesis loop?
All right, so that's something I haven't touched on yet, but I'm glad you asked. Let me show you a general schematic of the ammonia production process to illustrate the synthesis loop and how recirculation works.
All right.
Okay, here's the process flow diagram we looked at last time. We begin with methane, which is the primary component of natural gas. Through a process called steam reforming, we convert methane into hydrogen and carbon monoxide, which is then combined with air, and then methane is then oxidized into hydrogen and carbon monoxide, which is then transformed into carbon dioxide. So this is a combination of synthesis gas and carbon dioxide.
And the synthesis gas is what we fed into the Haber-Bosch reactor?
Correct. Before it enters the reactor, we use a scrubber unit, which removes the carbon dioxide to purify the gas mixture, ensuring we have high concentration of hydrogen and nitrogen, which are the key reactants for the ammonia synthesis.
So now we have the purified synthesis gas that is fed into the ammonia reactor.
Precisely. Nonetheless, before that, the compressor increases the pressure, and also the feed needs to meet a special condition in terms of temperature to make it like suitable for the reaction. And then finally it's fed into the PFR where the magic happens.
And how does the synthesis loop come into play?
Not all the nitrogen and hydrogen react on the first pass. So the unreacted gases along with the produced ammonia are cooled down, and the ammonia is separated out as a liquid. The remaining gases are recirculated back into the reactor. This recirculation or loop allows us to maximize the yield of ammonia by ensuring as much as possible conversion.
So the synthesis loop is an essential part of the efficiency of this whole process. Otherwise, we would throw away all the work done upstream before the reactor, right?
Absolutely. The synthesis loop is key to achieve high conversion rates and making the process economically viable. It is a critical aspect of the overall design and operation of the ammonia plant. The separation of ammonia in the downstream is energy intensive, but conceptually easily achievable due to the difference in the boiling points of hydrogen, nitrogen, and ammonia.
Okay, now that we have clarified what this synthesis loop means, maybe we can come back to this PFR concept, because you call it a concept, but I'm wondering how is it used in industry?
Yeah, that's right. The term PFR indeed is more a concept in chemical engineering that defines ideal conditions. In reality, industrial reactors designed to work as PFRs have to account for various practical and operational factors.
I see. What kind of factors are we talking about?
This is a good question. For starters, industrial ammonia reactors require robust design to handle high temperature, high pressure.
Yeah.
They must also account for the flow of gases, the catalyst bed. They should also account for heat expansion, mechanical stress, the heat removal due to exothermic reactions. So as you can see, many different factors. This leads us to the two main types of reactors in industry for this process, which are the tubular converters and the multi-bed converters.
Wow, that was a great overview. Maybe we can now go to these two reactor types.
Sure, tubular converters, once the industry standard, have tubes filled with catalyst where the reaction takes place. The cooling medium flows within these tubes to manage the reactor temperature. But these are mostly out of favor now due to their inefficiency and in large operation.
And nowadays?
Yeah, multi-bed converters are used, which are essentially a series of catalyst beds where the reaction progresses in stages. There are two main types, quench converters and indirect cooled multi-bed converters. In quench converters, after each catalyst bed where the reaction takes place, heat is generated. We inject cooler synthesis gas to bring the temperature down. This quenching, quote unquote, creates a zigzag temperature profile as we saw before, which keeps the reaction close to optimal rate. The quench gas mixing can be done with specific grids or by the placement of injection tubes depending on the design.
Sounds like a straightforward way to control the temperature.
It is, but it comes with a trade-off, Tim. Not all the gas interacts with the entire catalyst volume, which can lead to less efficient ammonia formation at higher concentrations. This means we often need a larger catalyst volume than in the indirect cooled variant.
And what about those indirectly cooled multi-bed converters?
These are the more modern approach. They use heat exchangers between the catalyst bed for cooling. The heat exchangers can be within the same vessel or separate, and they can use synthesis gas or even boiler feed water for cooling. This method is excellent for large capacity plants, and it's particularly effective when we want to use the reaction heat for generation steam.
This also sounds like a cleaner separation of concern for the reactor beds. So, is that why we're focusing on the indirect cooling for our simulation?
Precisely. Indirect cooled multi-bed converters are widely used in new plants and revamps due to their efficiency and effective heat management. They allow us to keep the reactor's volume compact while still handling the high gas flow needed for large-scale productions.
This really showcases the evolution of reactor design over time.
It does, and it's a great example of how chemical engineering continuously adapts to improve efficiency and meet the demand of modern production.
Yeah.
It's clear that the design and operation of these reactors is highly complex. Many studies have emphasized that the mathematical modeling is a reliable method to evaluate and optimize these systems.
That's true.
In fact, the overall economic balance of an ammonia production plant can significantly be affected by even slight increases in the conversion rates. Robust modeling therefore plays a key role in the analysis and design of these processes.
I see, yeah.
With this in mind, I'm curious, Tim, what we're going to learn in Rust today.
Yeah, but as we move from theory to practice, let me first express my gratitude to you, Jonathan, because your in-depth detailed modeling adds so much cool layers to our project, and I hope my zeal for exploration just had fueled this fire for or passion in you.
It's been an absolute joy, Tim. Unraveling the complexities of the Haber-Bosch process has been nothing short of exhilarating, a true testament to the spirit of engineering that originally inspired my career path.
Oh, happy to hear that. Now, turning our focus to Rust, let's examine our learning objectives. We aim to implement a nested data structure for configuring our Haber-Bosch reactor and streamlining this process. Therefore, we'll use the builder pattern. It is invaluable for piecing together complex objects. And Rust method chaining will afford us code that is not only functional, but also fast and very easy to read. Additionally, we'll deepen our skills with using Iterator function. And we join the venture to create our custom Iterator type to couple data and visualization.
That's impressive ambitions. I have to ask though, what is lifetimes in this context?
Yeah, lifetimes, that's a good question. They are a cornerstone concept in Rust. They act as a generic argument that informs the compiler of the duration a reference should remain valid. It's a bit technical, but we will link references to the Rust-lang book chapter.
That's a good idea.
For our purposes, lifetimes are used for our custom iterator and when we decompose our plotting functionality in multiple functions.
That's something to look forward to. I still wonder, Tim, how are we going to implement this step by step?
Let's have a look. Let's distill the essence of our approach with this visual aid. Each case study we undertake follows 3 steps. Initially, configuring our data structure, followed by running simulations, and culminating with the generation of visual outputs from our findings.
I see. The slide also indicates the 2 cases we want to show, right? Consider a reactor with a catalyst working at 200 bar and an alternative catalyst working at 100 bar.
Exactly, Jonathan. And the 3 pillars of our implementation, configuration, simulation, and visualization, are shown here. Each element will be encapsulated within its own dedicated module, ensuring a clean separation of concerns. As we proceed with today's session, we delve into the configuration module. This module serves as a bedrock, setting up the inputs required for the sequential simulation of our reactor beds. After simulation, the results are then organized within our data model, transformed through our custom-built iterators, and by this channeled into our visualization component. Now, let's dive into coding. Beware, before you implement Haber-Bosch sequential simulation and visualization on your own, that we raise the scope a lot of the series. So yeah, it may be worth to have a look at the solution once in a while. And yeah, that said, I think it's quite important to have fun learning, and so don't try too hard. And with that said, we can now hop into the actual code and get an overview. And here you can see our main function. And we will look at 2 case studies, differentiating in the catalysts. Therefore, we go over a loop of this case studies, have a configuration in a module, a simulation, and visualization. And each of them are in their own model. And own model means in different files. And so we will now go into the simulation module, and there you see, okay, I have something prepared here. We have like a new state vector. It has like 5 mixture components, which are our well-known nitrogen, hydrogen, and ammonia. And besides that, we have argon and methane as inerts, and we have a temperature. And for this, our Haber-Bosch model has more variables. You find most of them in the constants. What is quite interesting to highlight is we will support pressure changes, and we will have like a linear temperature model for the exothermic reaction. So it's quite simple, just a linear function, but better than nothing, right? And yeah, we also have a data structure that acts as solver infos, and this contains a model and the initial values for the solver. Okay, so with that, we see all what has been prepared in the simulation module, and we hop back not to the main, but into our configuration model. And here we have a catalyst enumeration to decide which catalyst we want to use. We have a Haber-Bosch bed setup data structure, which defines the setup for a reactor bed in our process. So here are here's a constant for the bed, depending on the catalyst, and also the density of the catalyst in this bed. And also we have like the temperature variables. Then there's a data structure that holds 2 containers, and these containers are the outputs of our ODE solver, like X out and Y out. We will get them from our ODE solver. And well, where we were working on next is like to get this Haber-Bosch instance running, like to get it up. And there's a difference here. Like we have no public variables, and that is actually quite good for encapsulation, because when you collaborate with other people and you are the implementer of that, you don't want to burden them with all the internal knowledge. So you have like private informations there. And like this course is about interdisciplinary and collaboration. So with this, we as an implementer can assure that nobody is able to change the catalyst after like all the simulation results are there. So there are no mix-ups. But what we will do next is we will implement our own builder pattern in Rust. Builder is used to construct complex projects, and we will now have a look. So there's another data structure needed, which like wraps our Haber-Bosch instance. And the nice part, and it's also related to encapsulation, is like the constructor. We have a possibility to change these variables. Also, they are non-public because Haber-Bosch instance builder is in the same module than Haber-Bosch instance. Okay, and what we will do now is we will finish this add-bed message, which is like quite easy. We access the work in progress object, and we got to the reactor bags. We push something here, and we just create a new bed setup. What's the name? Yes, Haber-Bosch bed setup. And now I can like control dot and fill struct fields. The nice thing is because this names equals the struct names, Rust knows automatically what to do, which is quite nice. And normally you could include a builder with a build pattern, which lets the type change to the building type. So here we consume self, like the builder will not be available anymore, and we will turn the instance we are building. And normally what you do in this build is like have some sanity checks. Like in our case, we could check what is about our beds. Are they empty? And if that's the case, we just tell the user a reactor bed is required. So at least one, right? And well, at the end, we have to return this object here. So now we're ready to hop to the main file and start to work on our loop. Because what we want to do is we want to configure this Haber-Bosch now. And for this we start with a for loop over a tuple of cut and file name prefix in studies. And with that we can say we want to have a setup or conf. And this is depending on the catalyst, we will build it differently, right? So we have this match arm with the two catalysts here, and we start with a k-mir, and here I will just instantiate the Haber-Bosch instance builder with a create function. We need the partial pressure, which is stored in our constants, and we need the catalyst, which is cut here. And then we can start to add beds, and we will use 2 here, and then we will conclude this by building. Okay, we need a semicolon here, and now it's complaining, okay, I don't know the variables, but I was smart, I just will now use copy and paste and conclude the rest. All right, with that done, we can now simply output our configuration, for example, to conclude this. We need to use this placeholder here to use the debug trait. And now we cargo run chb. What was it called? I don't know. Give me a sec. Sequential simulation. Double. Okay. Oh, we have errors. Yeah, we forgot to use the derive here. So that is a kind of error you will see when you forgot to implement a derive trait or a trait, and we can derive traits. Okay, so now let us see. And here, so you see, okay, we get like quite different values here for both. The beta is same, but yeah, that's concluding this part. We will now implement the sequential Haber-Bosch simulation. Sequential simulation means we simulate a reactor bed with an OD solver, and then for the next reactor bed we use these results to initialize it for the simulation. And yeah, for this we need to wire our Haber-Bosch instance with the simulation, and that's where we will start. We will have a look at the Haber-Bosch instance. I added some accessor functions for the length, for the cut, for the pressure. We can add new results to our method or our instance. What we need to do now is to implement the getSolverInfo method that is responsible for the wiring. And there we will start with a sanity check. So let us think, what can happen? We want the IDX to be greater than the length of the results, right? Because we actually have like the case either this index is 0, so we don't need previous results, or otherwise we need them. Not enough results. So if you think about it, if IDX is 0, length is 0, then IDX is not bigger. If length IDX would be 1 and length be 0, then we have a problem here. Okay. Next step, we create a model. Let model be just Haber-Bosch model. I have a new function for that, and there we can use self to fill it with some information. And for the bed setup, we just use reactor bed as a specific index. So that's how we create our model. That is really wiring the ODE solver. So that's nice. So we also need the starting conditions, like the x0. So let x0 equals, and they are two stage, right? As I said, IDX might be 0, so it's our first serialization. So we return 0 here, or we have to access the results. So we access the reactor results, and for this we use an iterator, and well, we use an index here. Like we use IDX -1, then we use the x out, and there we use the iterator. And we just know we need the last one, and we assume it's not empty. This unwrap, it is really getting it out. And now we get this error here, and it says like there are incompatible types from if and else. So we have like at one part we have the type it's not stated here, but as you can see, unwrap it well, you cannot see. But what this will return, if you can see it when you say let x equals to that. So it's a reference to F46, and we dereference this with the star, and the semicolon has to be gone. Okay, how much errors can you make in one line? So, and the same is true for y0. So we will start with a if statement, and we have like some values here. So in the initial case, we just take these partial pressures, and we multiply them by the pressure itself, and otherwise we have to select again like self, reactor results, IDX -1, y out, iter, last, unwrap, no semicolon. And then there's one special case. This is the temperature. We want to have the starting temperature from our reactor bed information. Okay, so here we access the reactor beds at IDX, and we use tstart. Okay, there's still something fishy. I see. We need to return this PP. Okay. And what is here the problem? Incompatible types again. I don't. I see. So you have to, that was a statement, so the semicolon. So I have to go into another line. That is a variable here. It has to be mutable. Now we make this mutable. And then we are ready to return our Haber-Bosch solver info. The nice thing is here, control dot, full struct fields, and it just works because we use the same names as in the struct. Okay, with that set up, maybe short info, we also have a print summary here. It will help us to check the results later. We can now move to the simulation. And in the simulation, we have a new function. It's called sequential simulation. It gets a mutable instance and a flag if we want to have a verbose output. And we just have to do some to-dos here. First of all, we have to go over a loop, and this loop is quite easy. We just say for IDX equals 0 up to the length of this Haber-Bosch instance for IDX in, and then we can use accessor here for the solver info. So we just say inst get solver info IDX, and now like the output is not nothing mattered. We did see this in the first video. Only thing to mention is like we assume that the maximum length will be 25. It's just to have a length measure, but the solver will end the simulation if it's like if there's no ammonia change before that. And yeah, so what we need to do here is to store results. And for this we add next results to our instance. And we get again like errors because of the type. We need a owned type, like not a reference. And at that point we have to clone, because there is no possibility to move that out of the solver. That would be quite neat. Maybe it will be added in this future. Okay, so with that we can go to the main and now just add sequential simulation here, and at that is called conf, and conf is not yet mutable. We need to be mutable to store the results, right? And verbose, it is just, let's start with false and hope for no errors. And this is actually a mutable conf reference. Okay, that works now. And then we can use this print summary on conf to get an output. And now I will run. And yeah, something's happening. That looks quite good, to be honest. That is the results we are expecting. And with this, the simulation module concludes. So, last but not least, the visualization module. I prepared a bit for us. So, like here we have some code that sets up the drawing area. I use this prepare chart function that was kind of a homework. We will have a look on it later in this section. And what we will concentrate on now is like getting these ranges that are marked by the to-do. For X, for now, we will just say, okay, it's probably something between 0 and 1. But for Y, we will implement a helper function, which is called getTemperatureRange and returns a range. Therefore, we use another dependency called Itertools, which will add additional functions to the iterators. For us, it's very interesting to have like a min-max function, which returns like the minimum and maximum in with one iteration. And yeah, to do this, we will get a result out, and we have to access the results and iterate over them. And well, to be honest, we need to iterate over this y outs in all the reactor beds. And for this, we use the function flatMap, which can flatten nested structures. Like we access now the iterators internally, and this is y out iter, and by this we now have like an iterator over our state vectors. So we can map this. We know at the 5th position we store our temperature. We want that as float 32, 4 bytes long for the plotting library. And we want to subtract 273 to transform it to temperature in Celsius. And then we're ready to hit the min-max by function, and we have to use by and give it another closure, because in the case of floats we have have some special cases, like it could be not a number and so on, and that is why Rust needs you to be very explicit about that. But there is help. What we can do, we just use the function partial compare from the left hand side on the right hand side, and this will like return an option that may be none, and we unwrap this option, so we assume it's never wrong, none. And we store this, and well, this min-max result itself is another enumeration. And yeah, let's see, we build a match arm over min-max-res. Control dot fill match arms, and that are the three cases we have. Like there's either no element, and in that case we just say the range goes from 0 to 1. It is one element, okay, so we give it a name, it's x, and then the range goes from x minus 0.5 to x plus 0.5. And yeah, like that is the most, let's say, relevant case. So there we just go from A to B. And with this we are ready to actually do the printing. We need to call the function first, then we will run. And now I can open these plots, and it's looking good. So there's something, so it's much bigger now, but there's something around 400 degrees, which sounds reasonable. All right, the next step is to get our line series ready. And for this, we will want to call this draw series method, like in the first part of the plotting. And the idea here is like our data model acts like the coupling point, and it will provide iterators, like tuples of x and a component of y. And we now want to implement this iterator. For this we switch into the configuration, and we see this code here prepared. So first there is a method iter my, which returns my iterator. And yeah, this is a lifetime generic. We talked about that shortly, and I will explain it a bit more here. And we have a type my iterator, and here we see again this lifetime generic, and it is actually used to tell Rust that we have like a reference to the Haber-Bosch instance, and this generic parameter really helps the compiler to figure out how long instance has to live. Okay, so in my iterator we need some variables. First of all, we want to have like a kind of input state. That is, first do we normalize, and second, the component index, which is a usize. And besides that, we need internal state to count our like counters for the iteration. First of all, we will go over containers, which are these results. Like each bed has its own result, so we have a container index or a bed index. Let's call it bed index. And we have element index. And yeah, this is like our iterator type with the variables. And in this method, we want to generate it. First of all, a small synergy check. If component is greater than 5, then we panic. Component too high. And otherwise we generate this my iterator. Okay, control dot to fill the struct fields, and here we can just F2, by the way, can normalize, be normalize, and then you see, oops, there's a new meaning. We can keep this name. The component index is component here. The bed index and the element index will be 0. And the instance is self. And that's why, like here, the lifetime is bound to self. So this is like the connection made. But to actually add functionality, we need to implement the iterator trait. And that is what we're doing now. We have to give the lifetime as generic argument. We implement for iterator. We implement iterator for our type myIterator. And here the generic lifetime parameter comes in play again. With control dot, we get this menu. I say implementing missing members, and we have like our to-dos. The type will be a pair of F32s, and our next function returns an option, which is none when there's no more item, or otherwise it will contain some pair. Okay? Let's first think about how we iterate over it. We will always erase the element index, and if we are out of elements, we will erase the bed index. So at the end, someday in the future, our bed index will be greater equal the length of the reactor results. And if that's the case, we want to return none. Else, we want to return some, and let's just put two values in here. Probably I have to write F32. I knew it. No, it's not working. What's the problem? We need to use a pair. Okay, so just to get the warnings, errors gone. And here we can now access our values. We access, well, let's have a first helper for the bed results. It is self instance, reactor results, and self bed IDX. And we will just take a reference because that's containing vectors, and copying is expensive. Sorry, I'm not used to this keyboard. And yeah, with the bed result, we can easily get X. We have like X out here. We use the element IDX, and we want this as F32. So X was easy. For Y, we will have a helper as a component, which is at bed res, Y out, self, and element IDX. And here you see the point is like a matrix. It's on the stack, so it's okay to have a copy. And now we want to have our Y value, and we have it mutable because we access it over the component with our element IDX. And now we have two cases. First of all, we either are searching for the component index 5, which is our temperature. And if that's the case, we want to change Y in the way that we just take a difference with 273, because that is in degrees Celsius. But else, if maybe we want to have a normalized component. So in this case, we need the sum. And here iterators are quite handy again, because we can iterate over our component vector, and we take the first 5. Because as you remember, we have nitrogen, hydrogen, ammonia, argon, and methane. And we need to map this. So our component is a reference to a F32, and we just make a F32 out of it. And then we take the sum. So Rust is still complaining because it's not quite sure if it's now which kind of floating number it is. But we can be explicit by just adding a double colon F32 here, and now we're ready. So we replace this with X and Y. And yeah, what happened is we are in an endless loop, so point to next element is what we need to do still. And for this, we have to increase the element index, right? And we have to go for sanity check because we don't want to have an element index that is longer than our results. If that's the case, we set element index to 0 again and increase the bad indice. So now we're ready because you see here bad indices improved and here the case is handled. So we can move back to our main function. Not yet. We still have to get an... that was the problem. Maybe some would have worked without a hint there. So we need to use an F32 here. And now here's no error anymore because the type is correct. Okay. So back in the main, we now can access our own custom iterator with the myIter function. And we select component 2. We want a normalization. And then we want to do a map because we programmed it in a way that we get x and one component of our state. But here we want to plot a component over another component. So we have like a pair here. And we can access the pair by using dot 1 or 2. And that's it. So that's one way to access ammonia. We use a slightly different way to access the temperature though. So temperature is at component 5, sorry. And yeah, here we use parentheses and we will just say that is x, that is t. And yeah, that's another way of writing it. I like that even more. And now we should be ready. Oops, fail click, terminal, cargo run. It is running, it is doing something. It is matrix index out of bounds exception and configuration somewhere. Okay, maybe it's like you have like a matrix here, right? I will just switch this to iterator to take the nth element because I know that's working because we have just one. We have just one dimension, so accessing it should work. Probably we have to map. No, we have to unwrap because this could fail, this nth. And this is reference. Okay, so there was a slight mistake. Hopefully it was the only one. At least it's not crashing anymore. Let's look at the plots. Okay, plots are still empty. What do we do? I think that's a good way to even see more of iterator usage. We will now collect a vector from the ammonia iterator. We just say it's a vec f32. And we actually have to clone the iterator. Okay. And then we will use a println and just dump our data to the terminal. Let's just be, let's lose this 2 for the temperature, because you never know which was the problem. Have a look at the values. Okay. So the temperature looks good. What is this? So this is quite high. We did something wrong with normalizing. Where's the problem? Ah, come on. That is the stupid one. We didn't divide it. Yeah, that's looking better. Yeah, here we go. So, we're ready to plot these diagrams. I want to conclude this part with looking a bit into this refactoring topic and lifetimes. So when we hop into the code, in our main function we have like a lot of rendering or plotting related code, and the other code it's much smaller, right? So what we want to do is like we just get nearly everything out here and move it into our visualization module. For this we come up with a function, we call it draw temperature over yield. So we're not doing too much here yet, so just copying, and now it's complaining because first of all we need a file name, which is a string, and second we need our, here it's called conf, we call it Haber-Bosch instance, and let's call it conf here too, like that's the type, right? And we don't need the string here anymore because that's already in the argument. And at the end we have the problem with the result type. So it doesn't know about our result. So we can copy it from here. And in this way we could be, we moved our small function. No, we also need information about the cut. But that's in configuration, right? Conf cut. Yeah, that is. Okay, so that was a simple refactoring, and as you can see, no lifetimes are here. We can just call it now here with draw temperature visualization draw. Ah, we forgot an important part. We need to make this public, otherwise other modules cannot access it. So visualization draw temperature over yield. We have a file name with this file name temp over yield, and we have the configuration. And here we don't handle the result type, so we need to use a question mark, and that's it, right? So we did the refactoring. But in your part, there was like, you were working with references of the shard context when you wanted to refactor the prepare shard method. So I want to shortly show you the prepare shard method here. And here you can see, okay, the reference is like bounded to the elements, but there are a lot of more generic arguments, and maybe, I'm not sure, maybe you can come up with better defaults when you more secure about your about what you're using, but that's, for me it was a bit tedious. So my idea, and what I saw a lot in other kinds of Rust, is that this, what we saw, this usage of closures, that's really helpful also in like don't need, like have user code that doesn't need lifetime, because you could have like a build chart method on your draw area which gets a closure that supports a builder and then generates a chart, or it doesn't need to like provide the builder. You could just instantiate your own builder. But probably that's good if you have like a template set, a theme set on the draw areas, and the draw area could creates a themed builder and you just use like caption and overload the defaults here. And then you could have like another method that takes the actual instance and is more like an adaptation on the ready instance. And in this way we could, at least in the user code, get rid of the references. So in the implementation of the library, you just still need, not references, lifetimes. You just need these lifetimes. Okay. So I hope you had a lot of fun with that. The concentration balance plots are open, but you can look at the solution, and we will now join Jonathan.
Hey Jonathan, great to meet again. Now, after we are capable to render these kinds of diagrams, what would you say are the next steps?
Hi team, these diagrams look promising.
Thank you.
For an in-depth analysis, we would now investigate sweet spot for our degrees of freedom. So first we have design parameters like the type of catalyst and the length of the reactor. Once we fix them, we cannot change them without significant cost.
True.
However, besides that, the effect of operational parameters, for instance, temperature, pressure, amount of inners in the fate of the reactor are important as well. And that's a lot to analyze.
That's true.
Therefore, I would propose to do a more in-depth analysis in our next video. These interactive elements you mentioned, I think they will prove to be quite
handy.
That's right.
So, that's the plan. But before, we will go into a holiday break. That means there will be a longer pause between this and the next video. With that said, feel free to subscribe to the channel to get a notification when the next video is up. And as always, if you have any questions, feel free to leave a comment. We are happy to help.
If you find this video informative and useful, we appreciate your recommendation.
And we hope you tune in for the next time. Till then, bye.
Bye bye.